Hi guys, my name is Abhidipto, and today we will be dealing with two major topics of electrostatics, that is Coulomb's law and Gauss law. Before we delve into the two, let's talk about static charges itself, right? So, let's say I have an isolated test positive charge, right? And the first property of this indivisible positive charge, right, is the fact that it has a specific electric field around it, right? Be it positive or negative. In this case, we're talking about a positive charge, right? It has a field emanating out of it, right? So in this case, if it's a positive charge, when we talk about the field lines, right? The field lines go outward, right? Infinite number of field lines perpendicular to the plane of the charge, right? Just move outward, right? And obviously, this is three-dimensional. I am showing it on a 2D plane, but these field lines, it's three-dimensional. They come out in all planes and all directions, right? And this is convention. Scientists consider the field lines to go move out of the positive charge, right? This is a total convention that we have formulated in the books of physics. And really, this is a specific field enclosed by the positive charge. Obviously, when we move radially outward from the charge, right, obviously the field strength decreases because, as usual, the field density decreases, right? So the density of the field lines decrease, hence the field strength decreases. So as we go farther away from the charge, the field strength decreases. But still, in simple words, we do have some sort of an electric field around this positive charge. So the way we represent it are basically, arrows coming out, pointing out of the charge, but perpendicular to the plane of the uh, charge. And obviously, these field lines to be kept in mind are three-dimensional and never cross each other, right? And when we are closer to the charge, the field lines are very dense, and hence the field strength is really high closer to the charge. However, as we move farther away or radially away from the charge, obviously the field density decreases and the corresponding field strength also decreases. But there is a certain area of influence around this charge. Hence, let's say we bring, another charge. If we take a test positive charge again, right? If we bring a positive charge closer to this charge, which we have already on board, right? Let's say this, let's call this as Q1, right? Let's represent this by Q1, right? This charge. So now, if I am bringing a test positive charge within the close vicinity of Q1, obviously there will be a mutual interaction between the two charges, right? So when I bring this test positive charge here, right, there is a mutual interaction with this positive charge. Why? Obviously, we know that even for this positive charge, right, field lines are moving outward, right, um, perpendicular to the charge, and there is an interaction of the field lines, right? Now these two field lines start interacting, right? And when they interact, obviously, there is this force, right? There is a force exerted between the two, right? And when I introduce this charge within the close vicinity of Q1, right, these field lines tend to align in a weird manner, okay? And that is where we have this crucial property of charges, right? And it's just how it is oriented now, right? These field lines, right? It's like uh, obviously in the case of two charges, right? Right? This is the way the field lines come out. Very interesting, right? Never gonna intersect, right? Never gonna intersect. But yes, the field lines, they arrive at a point where they move away from each other. This entire region, right, really it does not have a much field strength because the field density is low, right? And all the field lines are moving away. and this is how they start getting oriented, right? It's literally like, a tweak in the orientation. And I think this is very important to understand why these two charges will repel. That is where comes the concept of like charges and unlike charges. Like charges will repel and unlike charges will attract. In this case, we see that the like charges will repel, right? The two positive charges, they will repel because the field lines move outward and they try to oppose each other, right? And this is something which is very crucial. And we can connect this back to Coulomb's law. Obviously, we'll talk about the other case, but Coulomb's law, right? Coulomb's law is basically a law which devises a mathematical equation which says that the force between two positively charged, or between rather two arbitrary charged particles, not positive, it could be any charge. The nature of charge is independent, but force is K Q1 Q2 divided by the distance of separation squared, which is r squared. We consider it to be the radial distance between the two charges, right? So in this case, really, it's from the two centers of the charges. We take it to be r. So it's the separation distance between the two charges, and we square that, which is in the denominator. So k q1 q2 over r squared. This is the main formula of Coulomb's law, and Coulomb's law is helpful to analyze the forces, or we can even calculate the force between two positively or between two arbitrary charged particles. Okay, and yes, this K could also be represented as 1 over 4 pi E naught or epsilon naught, where epsilon is permittivity in space and it is also a constant, but really K and 1 over 4 pi epsilon naught, they're the same. Okay, and really this helps us to calculate the force between two charged particles, right? And in this case, we know we have two positively charged particles, so they will repel. And to be more specific, right, we know that force is a vector, right? Obviously, force is a vector, but it is not the nature of the charge that is deciding, uh, you know, the direction in this case. It does, but we have to maintain the absolute value. So we do have to have that absolute value because there is no meaning. For example, in this case, if I had a positive and a negative charge, right? Doesn't we can't have a negative force. That's not going to depict anything, right? It's not helping us to further analyze the situation. So we just take absolute value. We ignore the signs, right? So k q1 absolute value of q1 times absolute value of q2 over r squared. That is the electrostatic force between two charged particles, right? Whether it is attractive or repulsive, that depends on the nature of the charge, right? And from there, we can just kind of go back to E fields, right? E field, E field is nothing but force, right? Which is represented in newtons per coulomb of charge, per coulomb of charge. So really, if you think about the units, it is Newton per coulomb. Force per coulomb of charge. That is E field, right? So that is where E field comes from. And talking about forces, we get the force formula from Coulomb's law. Okay. Now let's get back to a bit of E fields. All right. Let's try to analyze a bit more of E fields, and then we will take it from there. Okay. So in this case, we had a positive and a positive charge. Let's say I had a positive and a negative charge. Obviously, two like charges, we know they repel. Positive charge, outward field, field lines, right? Field lines are just a representation of the field strength around the positive charge. While negative charge, right? Now negative charge, the field lines go inward. So there comes the point. The field lines are inward. This is convention. So when we talk about the interaction, if I bring any of the charges within the close vicinity of the other charge, so it's all gonna go towards the negative charge, outward from the positive charge and into the negative charge, right? So we know that there is a very strong field strength between the two charges, right? When we talk about the field strength, it is really strong between the two charges. There is no possibility for the field to be zero between the two. And again, E field, which is also a vector, is nothing but the SI units of E field is Newton per Coulomb, the force per unit of charge, right? So these are the field lines, okay? So the field lines for a positive charge, they move outward, for a negative charge, they move inward, and when you bring them in close vicinity, um, the field lines move away from the positive charge and into the negative charge, right? And yes, and there is an attractive force between the two particles. Obviously, if I know the amount, the magnitude of charge on each of them, I can use, and also if I know the separation distance, I can use Coulomb's law to identify the force between the two charged particles. And it is an equal and opposite force as per Newton's third law, right? It's an equal and opposite force. So the force that the positive charge exerts on the negative charge is the same as the force that the negative charge exerts on the positive charge, right? And in this case, it is an attractive force where the field lines move from the positive charge to the negative charge. So if taking that idea forward, right, again, these are point particles on a line, right? These are point particles on a line. Now, let's talk about a bit more of E fields, right? And that is how we depict the field lines, right? So really, I can figure out, field lines being vectors. I can figure out the force at this point, or not the force, but the E field, right? But let's talk about just a negative charge in itself, an isolated negative charge. Field lines moving inward, right? Field lines are moving inward into the positive charge, into the negative charge. So, if I want to find out the field strength is the field strength of this negative charge, let's say at this point, right? It is very important if we want to know what the field strength is, right? Now, obviously, we can even prove why the field strength. So let me call this what region 1 R1, and let this be R2, okay? And again, by definition, it is the force per coulomb of charge. But again, if we plug this in, right? Um, Now, for example, it is simple. If you want to analyze it, we can analyze it. Let's say we had, a positive charge or a negative charge at R1, right? Let's say I place a negative charge at R1, right? So if I want to know the field at R1 in itself, right? The field at R1, it is nothing but the force, right? Divided by the quantity of the charge, right? And this is something very interesting here, right? Because to figure out the E field, we need to have a test particle, right? That's the only way we can figure out the E field, right? And we'll get to a little more detail whether it is a vector or not. But when we talk about the E fields, right? Now, let me take this to be Q1 and let me take this to be Q2, right? Obviously, if I want to figure out the E field at R1, right, ER1, so then if I want to know the force, obviously as by definition it is the force per coulomb of charge. So it is force divided by Q2, right? Because that is the charge at R1. So now how do I know what the force is the question, right? So if I can simplify my expression, if I want to know how much is the force, right? Uh, it's a bit of an application here, right? Because, I have two charged particles, I can just use Coulomb's law. So K, Q1, Q2, right? Over, let's say R1, so we can take it as R1 squared. Let's take the radial distance to be R1. So R1 squared times, I can just multiply it by the reciprocal of the quantity of Q2, which is 1 over Q2, right? I can just put this in parentheses. You see the Q2s, they cancel out, right? So the field at R1, the field strength is KQ1 over R1 squared, right? That is the field strength. Now, if I want to figure out the field strength at R2, right, I can just again use the same equation. So E field due on R2, but obviously due to Q1, right, has to equal uh, force divided by whatever arbitrary charge. Let me take an arbitrary charge of Q3 at that point, because I need to have a charge at that point to devise or evaluate the field strength, right? Only then can a force act, right? A force can only act if I have a test on an arbitrary charged particle at that point R2, right? Obviously it is in the vicinity or E field of the negative charge, which is, I can again put this back to K Q1, which is because it's the field due to Q1 times Q3 over, let me take the radial distance to be R2, right? That was R1, now this is R2. So R2 squared, right? This is a subscript, right? Might be a bit confusing, but for now we can just take it to be R. So then it's more clear. So I'm taking this distance, right, from the center of the charge to R2 as small r. So I'll just remove this and write it as small r squared, right? And let me just erase this, right? So I can rewrite that. Oh, sorry, I have to just divide it by Q3 times 1 over Q3. Q3's cancel out, which is KQ1 over R squared, right? That is the E field at R2. That is, or rather, the field strength or the magnitude of the E field at R2. Okay. So that is the E field at the field strength at R2, and this is the field strength at R1. So E field at R1, this is E field at R2. Now the question comes, which one is greater? In which scenario do I have a greater field strength, right? Um, it is very important to understand that, right? And there comes the concept of, uh, again, we are obviously applying Coulomb's law here, but there just comes a bit of algebra, right? So, again, if I have a negative charge, right, field lines moving inward, right? If I have an arbitrary point R2, arbitrary point R1, obviously R1 is at a greater distance from the negative charge compared to R2. Let me take this distance to be R from R2, and that distance to be, as we solved it, R1 squared, R1, right? So we know that the E field at R2 is KQ1 over R squared, which we solved for. At R1 is KQ1 over R1 squared, right? Or it doesn't matter. I mean, we can just take it to be maybe even capital R, just for it to be a bit more clear. Maybe capital R works, right? Because it's at a greater distance, so it makes sense. So in that case, we know that capital R is greater than small r. So in that case, or in which scenario is the E field stronger? At R2 or R1? I know that it is KQ1 over R squared at R2. Again KQ1 over capital R squared at R1. KQ1, they are the same, so I can just strike them out. I don't have to worry about it. But, R is smaller. The denominator, right? Considering R to be smaller. So in this case, the denominator is smaller as compared to a bigger denominator, since capital R is greater than smaller. So if the denominator is smaller, the E field or this quantity will evaluate out at a much greater magnitude, right? If the denominator is greater, the fraction is of a much greater value, right? In this case, considering the numerators to be the same, if the denominator is smaller, I have a much greater E field, right? So from there, right, we can see that the E field from at R2 is greater than the E field at R1, right? And hence, we can conclude that the closer we are to the charge, stronger is the E field that we can that can be experienced, right? And hence stronger is the force, right? So we can go back and try to analyze vectors here. So obviously, the force between two charged particles, in this case a positive and a negative charge, right? The force is a vector. So electrostatic force, let me call it E force, is a vector. How about E field? Well, E field, right, is force per coulomb of charge, right? Rather Newton per coulomb, the unit. So in that case, I have a vector per unit of charge, which gives me a vector. So E field is also a vector, right? I'm not doing a dot product or a cross product in this case. Hence, E field is also a vector, right? I'm just dividing it by constant charge. So E field is a vector and E force is a vector. So in all these cases, we can represent it as a vector. Though in this case, we are only calculating the magnitude. Force over the charge, force per unit charge is the magnitude. Direction, we have our convention. Negative charge is inward, positive charge is outward, right? So here comes the helm. This is the helm of E fields and forces, right? So let's talk about another scenario and then we will take it forward from there. And anyway, from the previous case, what we saw, right? From the previous case, E field, right? Let's again write down the formula then for E field, right? We can just write down the formula for E field. So E field, right, is nothing but KQ, or rather the E field due to charge Q is KQ over R squared. Okay, this is the formula of E field, which is a vector. Obviously, in this case, we are interested in the magnitude of E field. Okay, so let's again talk about two charges, right? Let's take two positive charges. These are how the field lines align, right? I'll just make it simple in here so we get the idea. Pardon my handwriting, but I think we get the idea here, right? So now someone can say, just give me 1 minute. All right. Someone can say, um, the field strength, right? Is there a point where the field strength is zero, right? Is there a point between these two charges where we have an E field of zero? Hence, if we place any test charge, it experiences zero electrostatic force, right? So in other words, is there a certain point where I place a third charge which experiences net electrostatic force of zero, right? Is there such a location? Interesting. Field lines come outward, right? Field lines are always out of the plane, right? So Now, obviously, right, when we extend it, right, obviously it's not gonna we can't have a field line like this going, right, because they intersect, right. So that's null and void. We can't have a field line intersecting each other. But if we think about field strength, right, when we talk about a charge having a net electrostatic force of 0, right, we are really interested in such a location where the E field is 0, right. So if force is 0, right, if the force experienced by some arbitrary charge q is 0, that means that the E field at that location is 0. Hence, all we have to know where the E field is 0. There, if we place a third positive charge or a negative charge, right, the vectors cancel out, right? The force vectors will cancel out, hence it will not move, right? So, to know where the E field is 0, right, keeping in mind their vectors, really we want to know the location, right? Now, it has to be understood, or it is understood, that the E field will never be 0 outside the charges or away from the charges. In this case, like, somewhere here, somewhere here. It's not going to, be 0 away from the charges, because the field lines always move outward, right? If we even think by chance, let's say there is a field line of this test positive charge acting somewhere, let's say here, coming off. I mean, it's obviously infinite, right? It's not that the field lines end over here. We are just drawing it, restricting it to this space. But let's say there's some field line coming out in this direction from charge Q2, and let's call this Q1, right? And there is a field line even coming outward from this charge. So, right, in multiple directions. So there is no case, for the field lines to evaluate out to 0 at or cancel out each other's effect um, outside of these charges, right, away from these charges. It can only equal 0 between the charges, right, between the charges. Only then can it equal 0. And it is very evident when you draw it, because they move away from each other. So there must be some region over here where the E field is 0, right? And at that point, let's say the E field is 0 here. So at that point, right, if I place a third charge, test charge, be positive or negative, it will experience 0 force because the vectors cancel out. That's the beauty of this. So uh, if I have to find out that a point where the charges or the net field is 0, all I have to do is make an equation where the field due to Q1 should equal the field due to Q2, right? That is where we get this concept, right? Right. So the field due to Q1 should equal the field due to Q2, right? At that point where the two fields equal each other, right? Obviously, we know that they cancel out each other's effect, right? So we know that it has to be 0 somewhere here. So all we need to do is just make an equation and just solve for it, right? So in this case, what we would do is we would just, we know that it has to be in the middle. So let's say we take a point here at a distance of x from Q1. So I can just do KQ1 over x squared. And let's say the total separation distance is of 5 meters, right? Then in that case, I can just create an equation saying that KQ1 over x squared, the field due to Q1 at this point, let's say R, has to equal the field due to Q2. But what's the distance? If this is x, right? If this is x, and the total distance we know is 5 meters, it's 5 minus x, right? Squared. Obviously, the k's drop out. If we have the value of Q1, Q2, we just have to make the equation and solve for x. That is where the E field is 0, right? And really, that is where we get this concept from. Um, and it's really an application of the Coulomb's law, right? So yeah, once I know the value of Q1, Q2, right, it's gonna we can just frame this equation and solve for x. Similarly, let's talk about um, opposite charges. Let's say I have a positive charge and a negative charge. Field lines move inward, right? Right. Obviously, is there any point where, like the field line due to positive charge, right, is always moving outward, and due to the negative charge, it's always moving, outward from the positive charge into the negative charge, and also if we consider the negative charge is also moving into the charge, right, negative charge. So field line moving out of the positive charge into the negative charge at all points between the two charges, right? If we consider between the two charges, the field line is moving always towards the negative charge, right? So, there is no chance for the vectors to cancel out, right? The vectors don't cancel out between the two. It's all in one direction. Vectors only cancel out when they're in opposite directions, right? Only then can the vectors cancel, right? So, in which case does it cancel out? Well, that is very interesting. Let's take the positive charge, right, to be plus uh, 5 coulombs, the negative charge to be negative 3 coulombs, right? So it has been proved by scientists that the E field will be zero closer to the weaker charge. But before that, we have to understand the field lines outside. For the negative charge, they move inward. Positive charge is always outward. So if we think about the positive charge, the plus 5 coulomb charge, field lines at this point will be very weak, right? It's farther away. But for the negative charge, it's very, sorry, my bad for showing it in the wrong direction. For the positive charge, the field lines will be outward but very weak, right? But for the negative charge, it will be very strong. So the vectors, considering them to be in opposite directions, cancel out in this area. Obviously, yes, if we do have field lines coming outward here, and for the negative charge, the field lines will be very weak, but they won't cancel out. They only cancel out closer to the weaker charge. So let's say they are at a separation distance. Let's say the separation distance x is again 5 meters. Again, my equation will be the E field due to the positive charge q should equal the E field. That is when the E field, the magnitudes are the same and they cancel out. It's really, you can visualize it using forces. And K times 5 over R squared, right? Now for the positive 5 coulomb, the separation distance, right? The separation distance, obviously we know that between the two charges is 5 meters. But the field line is going to be an additional some r meters away from the negative charge. So when I do the equation, it will be 5 plus r whole squared, the net distance, right? Which will equal k times 3, the absolute value 3 over r squared, because from the negative charge it's just at a distance of r. You can create k's dropout. Considering it to be in one variable, you can solve for r, and that is where the E field is 0. All right. So this is an analysis of E fields and Coulomb's law, right, and a connection between the two. And in my next video, we will talk about Gauss law. All right. So stay tuned, and I will I will answer all your questions below in the comment section, and you feel free to watch my Gauss law video as well. Thank you so much.